Hi, my name is Peat, and welcome to my lab demonstration for Lab 3 of PHYS2212 at Georgia Tech. The objective of this lab is to use our cell phones and an app called Teslameter to explore the relationship between the separation distance and the magnetic field produced by a bar magnet. We're also going to calculate the magnitude of the magnetic field and the magnetic dipole moment, which is essential to determining the direction that the magnetic field moves in from north to south. We're also going to develop a computational model in GlowScript for the magnetic dipole moment and its influences on the magnetic field in space at an on-axis location perpendicular to the bar magnet and 45 degrees off-axis. The main physics concepts at play is the Biot-Savart law, which relates the magnetic fields to the currents producing the field, and you can also see that the magnetic dipole moment is in this equation, so we're going to be using it to solve for it. And yeah. We're also going to be looking at the distance dependence equation, which is given by k times r to the n. And lastly, we're going to be using the magnetic field of a dipole both on axis and perpendicular axis. A couple observations. When the magnetometer is really far away, the x component essentially goes to 0 because it's far enough to reduce its effect on the iPhone. And the opposite of this, when we move much closer, the x component of the magnetic field increases. So the first thing that we're going to do is compensate for the magnetic field, then we're going to locate the magnetometer in the iPhone, and we're going to read the distance on axis at each specific value from 20 to 220, and we're going to record this data in Excel. Then what we're going to do is we're going to plot our distance dependence equation logarithmically, so that we're going to linearize the displacement versus magnetic field. And here's kind of the two parts of our procedure. So you can see the results from the data are summarized here. We have all of our distances, which are then averaged, and the resulting magnetic fields, which are then averaged. And when these are all plotted at each distance in a logarithmic manner from the displacement to the magnetic field, it can be summarized into the equation y equals n log natural log of r plus natural log of k. So when you rearrange, we find k is equal to e to the power of negative 14.01. For data collection part 2, we kind of handle all of the off-axis figures, and the first thing that we do is we move the bar magnet out into a certain distance, and then we adjust the magnetic field by moving the iPhone, and then readjust to compensate for the magnetic field due to the Earth. The computational model essentially utilizes the Biot-Savart law to calculate the magnetic field due to each dipole at a certain observation location. Then here we handle the creation of different arrows using a relative position vector, and we have 2 on-axis arrows and 4 perpendicular arrows and 1 45-degree angle arrow. The blue arrows are the perpendicular ones, orange arrows are on-axis, and the purple arrow is the 45-degree one. So when we compare our models, we have the difference in the magnitude of the magnetic field at a 45-degree angle really isn't too significant. We have 3.96 times 10 to the negative 5 Teslas and 4.049 times 10 to the negative 5 Teslas. So this could be marked up to human error or just fluctuation on the Teslameter app. A couple critical questions. What if we hadn't oriented our experiment to compensate for magnetic north? What we would see is very inaccurate data because now we would have excess magnetic influence due to the magnetic north and we wouldn't have isolated the magnetic field of the magnet. If we were to stick two identical magnets together end to end and run the experiment again, we would expect to see a doubling effect in the magnetic field due to magnetic field superposition. Thank you.